Today we're digging into a paper that really feels like it could shake up the world of generative AI. It's called NextFlow. Unified sequential modeling activates multimodal understanding and generation.
Yeah, this one is a big deal. Basically shows that the architecture behind LLMs, the pure autoregressive or AR model, can finally be used for high-resolution vision.
Which has been the bottleneck for years, right? That computational inefficiency, especially at, the 1024 by 1024 resolution everyone wants.
Exactly. And the core innovation here is they've moved away from that slow, traditional raster scan approach
To this new thing they're calling a next scale prediction paradigm. That sounds like a fundamental shift.
It is, and the efficiency gain is it's staggering. NextFlow needs 6 times fewer FLOPs during inference compared to the big diffusion models like MMDIT.
6 times. And just to remind everyone, FLOPs are floating point operations per second. It's the main measure of compute cost. So what does that mean in real world speed?
It means you get a high quality image in about 5 seconds, which is,
Yeah.
older pure AR models could take over 10 minutes for the same thing. This is what makes it commercially viable.
And what's crazy is that it's only a 7 billion parameter model. Yet they're claiming it rivals the big diffusion models on quality and even gets the top scores on tough editing benchmarks like Embeddings.
And this is the real kicker. Because it's a single, unified AR system, it just naturally inherits these advanced capabilities like chain of thought reasoning and in-context learning for vision.
Okay, let's unpack that a bit. Why did we have the split in the first place? LLMs for text and logic and diffusion models for pretty pictures.
It all comes down to how they handle information. LLMs are sequential, discrete. Perfect for logic.
Yeah.
Diffusion models work in a continuous space, which is much better for, capturing the fine-grained texture you need for realism.
And the attempts to merge them, the hybrid models, they were always a bit clunky.
They were. You have this overhead from re-encoding these dual representations. And the pure AR models, well, they just hit a wall, that quadratic complexity from the raster scan approach.
Right. Generating token by token, row by row.
For a 1024 image, that's a sequence of tens of thousands of tokens. The attention calculation just explodes. You'd be waiting 10, maybe 15 minutes for one image. Nobody can build a product on that.
So that was the bottleneck NextFlow just smashed through. How did they actually build it? What's the architecture?
So these start with a standard decoder-only transformer, very much like an LLM.
Yeah.
And they were smart. They initialized it from Qwen 2.5 VL7B to get a head start on all that multimodal knowledge.
But the real magic is in how it handles the visual data, this
Yeah.
next scale prediction.
Exactly. So text tokens are predicted normally. But for images, instead of predicting the next token in one long flat sequence, the model predicts the entire token grid for the next resolution level.
Okay, so it's building the image hierarchically. It makes a rough 16 by 16 sketch and then uses that sketch to generate a more detailed 32 by 32 version and so on all the way up.
Precisely. It's like a pyramid. And because it's predicting scale by scale, the sequence length at any given step stays manageable. It completely sidesteps that quadratic explosion from raster scan. That's the source of the efficiency.
Got it. But to do that, you need a really good tokenizer, right? One that can handle these different scales.
They do. They use a Tokenflow-style Dual-Codebook VQ tokenizer. It's pretty sophisticated. It has a semantic codebook for the overall structure and objects.
And a pixel codebook for the fine details and textures?
You got it. And this is paired with multi-scale VQ to make sure the quality is high at every resolution.
Now, I've seen some research where a single branch VQGN actually gets better raw reconstruction scores, like a higher PSNR. Why go with a more complex dual codebook?
That's a great point. And you're right. On paper, a single branch VQGN can look slightly better for pure reconstruction.
Right.
What they found was the dual branch approach gives you a much better generative model. By separating semantics from pixels, you're kind of forcing a more meaningful structure onto the latent space. It makes the token space much easier for the autoregressive model to learn and predict. So you trade a tiny bit of reconstruction fidelity for a massive gain in learnability.
That makes sense. Okay, another complexity that jumps out at me is positional encoding. How does the model know that a token at position, say 11.1 in a 16 by 16 grid, is in the same spot as a token at 2 in a 32 by 32 grid?
That's where they did something really clever. They use what they call multi-scale 3D ROPE or rotary positional embedding.
Okay.
For vision tokens, it encodes 3 things: the X position, the Y position, and the scale. So every token has a coordinate like bpx by pstol.
And the key is that these coordinates are normalized, right?
That's the absolute critical insight. By normalizing the coordinates, every resolution maps onto the same fixed range, let's say 0 to C. So the model isn't learning new positions when it goes to a higher resolution. It's just learning to fill in more detail within the coordinate space it already understands.
Wow, so it completely avoids positional extrapolation. That's really elegant.
It is, and it's what lets them train across all these different resolutions so seamlessly.
Okay, let's talk about the training process, which the paper calls an odyssey. They were training progressively from 256 up to 1024, and they apparently hit a major wall. What happened?
It was a classic scaling problem. When they moved from 256 to 512 resolution pre-training, their Javel score, which measures quality, just plummeted.
Wow.
The sheer number of new tokens. At 512, you're adding thousands of extra tokens. And these tokens are mostly fine details. They're so numerous, they just completely drowned out the signal from the earlier, coarser scales and the loss calculation.
So the model basically forgot how to draw the big picture.
Exactly. The early scales determine the fundamental structure, where the person is, what the background is, but they have very few tokens. The model just started ignoring those few critical tokens and only optimized for the thousands of little texture tokens. You got images with weird artifacts and broken compositions.
So how did they fix that? It sounds like a tricky balancing act.
They called the solution scale reweight. They just assigned weights to the loss at each scale, where the weight is inversely proportional to the number of tokens at that scale.
Ah, so you make the model care way more about getting those first few coarse structural tokens right.
Precisely. It's like building a house. You put all your effort into making sure the foundation is perfect before you worry about the wallpaper. It stabilized the whole process and got rid of those artifacts.
Okay, that's one hurdle down. The next one they mentioned is a classic AR problem, exposure bias.
Yeah, exposure bias is a killer. The model trains on perfect ground truth data, but at inference time, it has to rely on its own messy, imperfect predictions from previous steps. One small error early on can snowball into a disaster.
And they tried a standard fix self-correction, but it actually made things worse. Why?
Because in older AR vision models, the input features would accumulate from every previous scale. This created this incredibly complex, high-dimensional feature space. When they tried to apply self-correction in that messy, accumulated space, the whole thing just fell apart. The feature space was too complex.
So what was the fix?
Something beautifully simple. They changed the visual input to use residual features directly from the codebook with no accumulation.
Ah, so you drastically simplify the input feature space.
Exactly. By constraining the input complexity, the self-correction mechanism suddenly became super effective. Performance shot up and local artifacts went down. A really clean solution.
And finally, they used reinforcement learning, GRPO, which is common for LLMs. But again, you have that problem of the fine detail tokens dominating the optimization.
You do. So they used a prefix-tuning strategy. They basically froze the learning for the last 8 or so scales, those that handle all the fine detail, and only applied the RL optimization to the first few coarse, low-resolution steps.
So you focus that powerful but noisy RL signal only on the most important structural decisions.
Right. You're teaching the model to make better choices about the overall layout and semantics without messing up the fine-grained texture generation it already learned during pre-training.
That makes a lot of sense. So stepping back, we know the VQ tokenizer is efficient, but it's discrete. It loses some detail.
It's the trade-off, yeah. To get around that, they built an optional diffusion-based decoder. It's purely for refinement.
To add back that photorealistic detail, especially for things like faces or text.
Exactly. It takes all the outputs from the AR model, the semantic embeddings, the pixel embeddings, and uses them to condition a diffusion process for that final polish.
And how did they feed the information in? I saw a note about a crucial design choice there.
Yes. The discrete tokens are injected only through the visual conditioning branch. They found that if you mixed the discrete tokens in with the text prompt embeddings, it would actually corrupt the semantic meaning and hurt the model's ability to follow the prompt.
So there's a clear choice for the user. If you need maximum photorealism, you turn on the diffusion refiner.
Right. But if you're doing something like local editing, where you need perfect spatial consistency, you stick with the VQ decoder because it's deterministic. The diffusion output is stochastic, it can change things slightly.
In fact, they disabled the diffusion decoder for most of their reported editing benchmarks, right?
They did, which really proves the strength of the core AR model. The refiner is just an optional extra.
Let's talk about the engineering for a second. Training on 6 trillion tokens with over 1,000 GPUs is Wow, it's a massive undertaking.
It's huge. And they had to invent some clever solutions. The first was workload balancing. Standard data packing, where you just fix the sequence length, was really inefficient because their data was so varied. Text, images, different resolutions.
Ooh, some GPUs would finish early and just sit there idle.
Constantly. So instead, they developed fixed max computation budget packing. They estimated the FLOPs required for each sample and packed batches to have an equal computational load, not an equal length.
And that gave them a 4.1x speed up.
4.1x speed up. It's an incredible number. It just goes to show how much performance is left on the table in the data engineering, not just the model architecture.
The other innovation was about memory.
Right. The VQ codebook is massive, so the final logit tensor for the loss calculation was eating up a ton of memory. They used something called fused linear cross entropy.
Fusing the last linear layer and the loss calculation into one kernel.
Exactly. By doing that, they never had to actually store the full gigantic logit tensor in memory. It saved them about 20 gigabytes per GPU, which at that scale is absolutely critical.
Okay, let's circle back to that 6x fewer FLOPs claim. Can you break down where that comes from?
Sure, you can split the cost into two parts: the linear FFN layers and the quadratic attention mechanism. For the linear parts, NextFlow has a 7.2x advantage.
Because it's only processing the tokens for the current scale, not the whole image at once, like a diffusion model.
Precisely. And for the quadratic attention cost, even with KV caching, the cumulative sequence length in the diffusion model is just much, much larger than what the AR model sees at each step. This gives NextFlow about a 4.7x advantage on attention. Add it all up, and you get that massive overall efficiency gain.
The efficiency is clear. But what about the quality? The paper shows SOTA scores on DPG and Genemal, but I was really struck by its performance on the WISE benchmark.
Me too. A score of 0.62 on WISE is really impressive. It shows the model has a deep understanding of the world culture, space, physics. That's the LLM architecture paying dividends. It's not just a pixel pusher. It understands semantics.
And that semantic understanding seems to be why it's so good at editing.
I think so. That iterative fine-grained control makes it incredibly precise. On Embeddings, it got the highest overall score, 4.49, and it just dominated the adjust and remove subtasks.
The subject consistency comparison against models like GPT-4 was also pretty eye-opening.
Yeah, that SC score of 9.22 for preserving a subject's identity is top tier. It even edged out GPT-4o, which scored 9.03. For any kind of commercial use, brand assets or character design, that kind of consistency is non-negotiable.
And they even built their own benchmark edit canvas with 56 different tasks, and it came out on top there, too.
It did. It showed particular strength in subject-driven generation. It just confirms that the architecture is fundamentally well-suited for complex, precise editing.
Which brings us back to the biggest prize, the emergent capabilities you get from this unified structure, this ability to think.
It's incredible. The first is chain of thought reasoning. You can ask it for China's national treasure, and instead of just guessing, it will output its reasoning. This is ambiguous. It could be the red panda or the giant panda, but the giant panda is more widely recognized, and then it generates the giant panda.
And that reasoning process actually improves its performance.
Massively. The COD fine-tuning boosted its WISE score from 0.60 to 0.70. It also gets in-context learning. You can show it a before and after example of a style transfer and then give it a new image, and it can apply that same style, zero shot.
Because it's all one continuous data stream for the model.
Exactly. It just sees a pattern and applies it. And that leads to interleave generation, creating stories or instructions with alternating text and images. All of this comes almost for free from the unified AR architecture.
So to wrap up the main findings, NextFlow seems to have successfully built a single AR framework that is incredibly efficient for high-res generation, rivals diffusion on quality, and brings a whole new level of reasoning and editing to the table.
That's a perfect summary, but we should touch on the limitations. The VQ Tokenizer, for all its benefits, is still a bottleneck.
Yeah.
You sometimes still need that diffusion refiner for true photorealism, and balancing text and vision objectives in a single 7B model is still a really hard problem.
So where do they go from here? The paper lays out a few future directions.
Three main paths. First, just scaling the model. They think mixture of experts frameworks could yield big gains. Second, better tokenization. Developing tokenizers with higher compression rates would just compound all the efficiency gains they've already made.
And the third one sounds like the most exciting.
It is. It's native multimodal CoT and unified RL. Because the whole system is autoregressive, you can apply standard LLM reinforcement learning techniques directly to the model's entire reasoning and generation process. You can teach it to think with images in a way that's just not possible with hybrid models.
So given these efficiency gains, we're talking 224 by 124 images in 5 seconds. With this level of quality and reasoning, how quickly do you think we'll see this AR architecture start to dominate commercial apps that need fast, interactive, high-res generation? That's the question to chew on now.